March 23, 2009, Narita, Japan, 6:49 a.m. A 200-ton cargo jet, upside down, on fire, 2 pilots dead. The whole sequence, 10 seconds, a bounce, a wrong input, a wing snapped clean off. This was not the first time. Same airline, same plane, same crash, 12 years earlier. How does an airline lose the same aircraft the same way twice? The answer starts in the middle of the night, about 4 hours before that fireball on the runway. At 2 in the morning local time, a FedEx MD-11 freighter pushed back from its gate at Guangzhou Baiyun International Airport in southern China. The flight number was FedEx 80, a routine overnight cargo run, one of hundreds that kept the company's global network moving while the rest of the world slept. Inside the cockpit were 2 pilots. The captain was a 54-year-old former Marine Corps fighter pilot who had been with FedEx since 1996. He had more than 12,800 total hours, including over 3,600 on the MD-11. Colleagues described him as steady, methodical, someone who flew by the book. His background included years of landing fighter jets on aircraft carriers, the most demanding flying environment on Earth. The first officer was 49, a former Air Force C-5 Galaxy pilot who had joined FedEx in 2006. He had over 6,300 hours total, but only 879 on the MD-11. By most standards, that made him competent, but still relatively new on the type. And there was one detail about this first officer that mattered more than his total hours. Because he usually flew as a relief pilot on long-haul flights, taking over during crews while the other crew rested, he rarely handled takeoffs and landings. In the 2.5 years since his conversion to the MD-11, he had averaged just 2.5 landings per month. That is not a lot of practice for an airplane that demands precision every single time. And that distinction matters more on the MD-11 than on almost any other airliner in the world. On a Boeing 767 or an Airbus A330, a pilot who has not landed in a few weeks can usually get back into the rhythm within the first few seconds of the flare. Those airplanes are forgiving. They respond predictably. They give pilots time to correct. The MD-11 does not. It crosses the threshold at 155 to 165 knots, 10 to 20 knots faster than comparable wide bodies. That extra speed means more kinetic energy at touchdown, tighter margins for error, and less time between a small mistake and an irreversible one. A pilot who lands this airplane regularly develops a feel for its quirks. The slight delay between input and response, the tendency to float when the nose comes up, the way a firm touchdown can launch it back into the air if the pitch is not exactly right. A pilot who lands it 2.5 times a month is essentially relearning those quirks every time. The aircraft itself was registered November 526 Foxtrot Echo. It had rolled off the McDonnell Douglas production line in 1994 as a passenger MD-11 and lived several lives since, including a stint as a NASA test bed before Delta Airlines flew it for 8 years. FedEx acquired it in 2004, converted it to a freighter, and put it into cargo service. By March 2009, it was a well-worn but capable machine, one of dozens of MD-11's that formed the backbone of the company's long-haul fleet. But the MD-11 was not just any airplane. Born in the late 1980s as a stretched, modernized successor to the DC-10, it was McDonnell Douglas's attempt to compete with the Boeing 777 and the Airbus A340. The engineers had fitted bigger, more powerful engines and added a modern glass cockpit that allowed a 2-person crew instead of 3. But to squeeze out the range and efficiency numbers they had promised to airlines, they also made a compromise that would define this aircraft's entire reputation. They reduced the size of the horizontal stabilizer, the small wing at the tail that controls pitch, to cut drag. And the way weight was distributed along the long fuselage created what pilots called a barbell effect, making pitch input sluggish to start and hard to stop once they got going. To compensate, McDonnell Douglas installed a computerized system called LSAS, the Longitudinal Stability Augmentation System, which was supposed to smooth out what the aerodynamics alone could not fix. On paper, it worked. In practice, it gave pilots an aircraft that always seemed to be one step ahead of them. On approach, it carried more momentum than crews were used to. In the flare, it demanded precision that no other airliner required. And if something went wrong close to the ground, a bounce, a gust, a late correction, things could unravel faster than a human could react. FedEx knew this. By 2009, the MD-11 had one of the worst hull loss rates of any modern jetliner. More than a dozen major accidents and incidents, many of them during landing. A China Airlines cargo MD-11 had broken apart after a bounced landing in Hong Kong in 1999, killing 3 people. And FedEx's own history with this airplane included an accident that should have been a permanent warning. On July 31, 1997, FedEx Flight 14, another MD-11 freighter, touched down hard at Newark Airport in New Jersey. The captain, worried about running out of runway, pushed the nose down while the main gear was still in the air. The plane slammed back onto the runway with more than 3 times the design load on the landing gear. The gear collapsed. The aircraft flipped upside down and caught fire. Both pilots escaped with minor injuries. The airplane was destroyed. After that crash, the FAA ordered all MD-11 operators to train their pilots in a bounce recovery technique. Hold the pitch at 7.5 degrees. Add power. If things get unstable, go around. Simple rules. Both pilots on FedEx Flight 80 had received this training in their simulators back in 2006. They knew the drill. But the training had been given once, just once. It was not part of their recurrent training, and it had been 3 years since either of them had practiced it. Inside the cockpit of Flight 80, none of this history felt urgent. The departure from Guangzhou was routine. The 3.5-hour cruise over the South China Sea was uneventful. Air traffic control handoffs came and went. The autopilot held course and altitude. But about 45 minutes before landing, the cockpit voice recorder captured the first officer telling the captain that they were both tired. The captain agreed. The first officer added something along the lines of, "If it gets too quiet, make some noise." An offhand remark, a common strategy among cargo pilots who fly through the body's natural low points. Neither pilot was unusually sleep-deprived by the standards of their profession, but investigators later found that neither could have had more than 4 hours of consecutive sleep in the 24 hours before this flight. The investigation would later piece together their rest patterns through hotel records, credit card transactions, and other signs of activity. The picture that emerged was typical for long-haul cargo crews, but far from ideal. Both pilots had been flying daytime schedules during their rotation in Asia, which meant their circadian rhythms were partially adjusted to local time. But this flight departed at 2 in the morning, the deepest trough of the body's natural sleep cycle, regardless of time zone adaptation. Physiologically, fatigue at this level can look a lot like mild hypoxia. Reaction times slow, scan patterns become less thorough, small cues that would normally jump out, a slightly high sync rate, a drift off the center line, an airspeed needle trending the wrong way, start to blend into the background noise of a routine flight. The dangerous thing about fatigue is that it erodes judgment before it erodes awareness. A fatigued pilot can feel alert enough to fly while simultaneously losing the capacity to catch the one thing that will matter most. And they were now heading into the most demanding phase, a gusty, turbulent approach, at the exact moment when their mental sharpness was most likely to be compromised. As Flight 80 descended into Narita's morning airspace, the wind was the first thing that demanded attention. It was blowing from the northwest at around 26 knots, gusting as high as 40 and dropping as low as 16. That is, a spread of more than 20 knots between the peaks and the lulls. To understand why this mattered, you need to know that an airplane flies relative to the air around it. If the headwind suddenly drops by 15 knots, the aircraft's airspeed drops by 15 knots, instantly, and with it, the lift keeping the plane in the air. In gusty conditions, the airspeed needle swings constantly, and the pilot has to chase it with thrust and pitch adjustments just to keep the airplane on a stable path. If you're enjoying this video, consider subscribing to the channel. It helps us keep telling these stories. Now, let's get back to the cockpit. At 6:43, air traffic control relayed a pilot report from a Boeing 747 that had just landed on runway 34 left, the same runway Flight 80 was approaching. That crew reported wind shear of plus or minus 15 knots below 2,000 feet. The captain noted the report and decided on a speed additive of 10 knots above the reference landing speed, setting their target at 164 knots. A reasonable call. The winds were strong, but not beyond the aircraft's published limits. Planes had been landing all morning. At 6:44, the captain advised the first officer to check the wind shear guidance on their displays, and the first officer confirmed it. At 6:45, the tower updated the winds again. 320 degrees at 26 knots, gusting 38, minimum 16. The spread was widening. A minute later, they received a pilot report from the aircraft landing just ahead of them. A cargo 747 that had encountered fairly strong turbulence, with wind fluctuations of plus or minus 15 knots below 1,000 feet. This was consistent with what they had already been told, but hearing it from a crew that had just been through it added texture to the numbers. The air below them was rough and getting rougher. The first officer set the flaps to 35 degrees, and the captain completed the before landing checklist. Everything was done by the book. Everything was on schedule. And yet every piece of information they received in those final minutes was telling them the same thing. This was not going to be a normal landing. 3 minutes later, at 6:46, the tower cleared Flight 80 to land. Winds were now 320 degrees at 29 knots, gusting 36, minimum 17. The captain confirmed the runway, then said one word with enormous weight behind it: stabilized. And then he laughed. A small, tired laugh. The kind pilots use to acknowledge a challenge without letting it overwhelm them. It was not carelessness, it was coping, but the approach was not stabilized. The airspeed was swinging well beyond the plus or minus 10-knot window that defines a stable approach. At 500 feet, the gate where that decision had to be made, the numbers were outside the criteria. A go-around was an option. If they had taken it, they could have held in the pattern, waited for conditions to improve, or diverted with plenty of fuel to spare. But that call did not come. Both pilots believed they could land this airplane. Plenty of planes before them had already done so that morning. And this is where hindsight makes things look simpler than they were. From a distance, it is easy to say they should have gone around. But from inside the cockpit, the decision is far less binary. Airlines teach stabilized approach criteria as a clear line. You are either stable or you are not. But in gusty conditions, every number moves. The airspeed needle swings up and down. The sink rate fluctuates. The localizer drifts. If pilots executed a go-around every time a gust pushed one parameter outside the window for half a second, they would never land during certain weather conditions. And wind is often widespread. Diverting to an alternate airport might not make things any better. So in practice, pilots judge the average. They look at the overall picture. They ask themselves, over the last 30 seconds, has this approach been tracking toward a safe landing? The answer on this morning to these two pilots was yes. The winds were high, but not beyond limits. The gusts were uncomfortable, but not unprecedented. The aircraft was on the glide slope and roughly on speed when averaged over time. They had fuel to hold, but no guarantee that holding would improve conditions, so they continued, and it is hard to blame them for that decision. The problem was not the decision to land. The problem was what happened in the last 10 seconds, and the airplane they were trying to land when it happened. But those planes were not MD-11's. As the aircraft passed 200 feet, the first officer disconnected the autopilot and took manual control. The airspeed was 178 knots, 14 knots above their target. By the time they reached 100 feet, the wind shifted, and the speed plummeted to 154 knots, 10 knots below target. In 4 seconds, the airplane had lost 24 knots of airspeed, and then, at 50 feet above the runway, the auto throttle did exactly what it was programmed to do. It entered retard mode, a setting designed for auto-land approaches, and began pulling the engines back toward idle. The system did not know the first officer was hand-flying the airplane. It did not know the airspeed was already dangerously low. It simply executed its programming. The first officer needed thrust. He did not add any. This was one of the MD-11's most dangerous design quirks, and it had been known for years. The auto-throttle's retard mode had been programmed to match the touchdown requirements for an auto-land, a landing flown entirely by the autopilot. During auto-land, the system worked perfectly. The autopilot controlled the pitch, while the auto-throttle smoothly reduced power. But when pilots hand-flew the approach with the auto-throttle still engaged, which was standard procedure at most airlines, the auto-throttle would still begin pulling power at 50 feet, regardless of what the pilot was doing with the yoke. The result was an airplane losing thrust at the exact moment the pilot needed it most. There was one airline that never suffered a serious landing mishap with the MD-11, American Airlines, and their procedure was different from everyone else's. American disconnected the auto throttle before landing and flew the final approach entirely by hand. Whether that single procedural difference was the reason for their clean record was never proven definitively, but the correlation was hard to ignore. The altitude callouts came in rapid succession: 50, 40, 30, 20, 10. At 30 feet, the first officer should have begun his flare, a smooth pull on the yoke to raise the nose and slow the descent. He started at 20 feet, 1 second late. Recognizing he was behind, he pulled harder than normal. The nose rose to 4.6 degrees, too high. Fearing a tail strike, he immediately pushed the nose back down. And in that moment, in the split second between pulling too much and pushing too far, the accident sequence began. At 6:48 and 20 seconds, the MD-11 strikes runway 34 left at 166 knots. The flight data recorder measures 1.63 Gs. The plane bounces back into the air, and here is where the MD-11's design makes everything worse. The cockpit of this aircraft sits nearly 100 feet ahead of the main landing gear. When the gear hits the runway and bounces, the back of the plane rotates upward, while the front continues on its original trajectory. From the pilot's seats, it feels like a firm but normal touchdown. The first officer does not realize the main gear has left the ground. He pushes the nose down, the way a pilot would during a normal landing rollout, to lower the nose wheel onto the runway. But the nose wheel is not near the runway. The airplane is airborne, and that nose-down input drives the aircraft back toward the concrete nose first. At 6:48 and 22 seconds, the MD-11 slams onto the runway on its nose gear. The pitch angle at impact is negative 1.8 degrees, nose down. The vertical acceleration spikes to 2.21 Gs. The nose bounces violently upward. The pitch swings to 6.7 degrees. The airplane launches back into the air, 16 feet above the runway, higher than the first bounce. More energy, more danger. This is the last chance. 16 feet of air, enough time to add power, enough time to call go around, enough time for the captain to grab the controls and say my aircraft. None of these things happen. Instead, the first officer's hands do what instinct tells them to do. The nose is pitching up. He pushes it down, full forward on the yoke. The pitch swings from 6.7 degrees nose up through 0 and keeps going. Negative 4.9 degrees nose down. The airplane is now diving at the runway from 16 feet. At 6:48 and 27 seconds, the third impact comes. The nose gear hits first, then the left main gear, then the center and right. The G-meter spikes past 3.06. The left main landing gear drives upward into the wing with a force more than double its design limit. The wing spar, the main structural beam of the wing, fails instantly. The left wing begins to tear away from the fuselage. 50,000 pounds of jet fuel spill from the ruptured tanks into a shower of sparks from scraping metal. The fire is immediate and massive. With the left wing gone and the right wing still generating lift, the airplane rolls violently to the left. The cockpit voice recorder captures a bang, the master warning, and the captain's final words: "Fire, oh shit." The ground proximity warning screams bank angle, and then the MD-11 flips completely upside down, slides off the runway, and comes to rest inverted in the grass, engulfed in flames. The tower controller activated the crash alarm before the aircraft had stopped moving. Fire trucks reached the scene within a minute, but the blaze was so intense that firefighters could not reach the cockpit for nearly 40 minutes. By then, both pilots were gone. Captain Kevin Mosley died from injuries sustained during the impact. First Officer Anthony Pino died from smoke inhalation. They were the only two people on board. FedEx Flight 80 was the first fatal jet accident in FedEx's history, and it happened on an airplane whose tendency to do exactly this had been documented for over a decade. The Japan Transport Safety Board spent 4 years investigating this crash, and what they found went far deeper than one pilot's inputs on a gusty morning. The direct cause was clear: the first officer's large nose-down elevator inputs before and during the first touchdown, followed by the same instinctive nose-down response during the second bounce, created the porpoising sequence that destroyed the aircraft. The captain's failure to intervene at any point during the 10-second sequence was cited as a contributing factor. On this point, investigators were careful not to assign blame in the way the public might expect. The captain was the pilot monitoring. His job was to back up the first officer, call out deviations, and take over if the situation demanded it. At no point during the 10-second sequence did the captain call out the bounces, announce a go-around, or take control of the aircraft. But investigators noted that the entire sequence, from first touchdown to wing separation, lasted less time than it takes to read this sentence aloud. The porpoising developed so rapidly that by the time the captain could have processed what was happening, the situation was already beyond recovery. Whether fatigue slowed his reaction, or whether the speed of events simply outpaced any human response, could never be fully determined. What was clear was that the system, the training, the procedures, the design of the airplane, had placed both pilots in a position where 10 seconds of imperfect inputs could destroy an aircraft. And that was not a problem any single pilot could solve alone. So were the gusty winds and the fluctuating airspeed. But the investigation also exposed the fault lines beneath the surface. The bounce recovery training that both pilots had received, the training implemented specifically because of the Newark crash 12 years earlier, had been given once. A single simulator session in 2006, not repeated, not part of recurrent training. When the first officer needed that training most, in a moment of surprise and high workload, 3 years had eroded it to nothing. Instinct overwrote procedure. He pushed the nose down because that is what the human brain tells you to do when the nose pitches up. The training was supposed to override that instinct. It did not survive the gap between the classroom and the cockpit. The JTSB also found that the landing gear itself carried a hidden flaw. Under FAA certification rules, the gear was required to break away from the wing without breaching the fuel tanks if the maximum load was exceeded. But that requirement assumed a horizontal impact, like striking an object on the runway. Under a purely vertical overload, the kind that happens in a hard landing, there was no guarantee the gear would separate safely. On Flight 80, the gear did not shear away. It drove straight up through the wing, snapping the spar and rupturing the fuel tanks. If the gear had failed as designed under a vertical load, the wing might have settled onto the runway intact. The plane might have stayed upright. The pilots might have walked away, exactly as the pilots of FedEx Flight 14 had walked away in Newark 12 years before. That was the cruelest symmetry of all. The same airline, the same type, the same sequence. One crew survived because the plane stayed upright long enough to escape. The other did not. Investigators also ran simulations that revealed something remarkable. If the auto ground spoilers had deployed in 0.6 seconds, instead of 1.2 seconds after the first touchdown, the dampening effect during those extra 0.6 of a second would have changed the entire outcome. The first bounce would have been smaller. The porpoising would not have developed. The airplane would have rolled out normally, 0.6 of a second. That was the margin between a routine landing and a fatal crash. The investigation also uncovered a structural truth that connected Flight 80 to every MD-11 hard landing that had come before. When the landing gear on most modern airliners is overloaded beyond its design limit, it is built to shear away cleanly, breaking at predetermined fuse pins that allow the gear to separate without puncturing the fuel tanks in the wings above. This is a critical safety feature because a gear collapse that ruptures a fuel tank almost always leads to fire. But the MD-11's landing gear had been certified under an older interpretation of the rules. The fuse pins were designed to fail under a horizontal load, the kind of force that would occur if the gear struck an obstacle on the runway. Under a purely vertical overload, the kind that occurs during a catastrophic hard landing, the pins held. The gear did not separate. Instead, it drove straight upward through the wing structure, snapping the spar and tearing open the fuel tanks. Fire erupted instantly. By 2009, the FAA had long since updated its interpretation to require that gear fail safely under vertical loads as well. But the MD-11 had been certified before that change, and no one had required a retrofit. The airplane was legal, it just was not safe. Not in the one scenario that kept happening to it over and over again. After this accident, and a similar crash of a Lufthansa cargo MD-11 in Riyadh in 2010, where both pilots survived, Boeing hosted a conference of all MD-11 operators. The manual was rewritten. the flare height was raised. The bounce recovery procedure was replaced with a simpler instruction. If you bounce, go around. No judgment call, no technique to remember from a simulator session 3 years ago. Just go around. FedEx overhauled its training program entirely. Recurrent bounce recovery practice was added. A module was created to help pilots understand how the MD-11's long fuselage distorts what they feel in the cockpit. Head-up displays were installed on every MD-11 in the fleet, and the JTSB recommended that Boeing reduce the spoiler deployment time, install a gear touchdown indicator so pilots could see whether their wheels were actually on the ground, and find ways to limit large nose-down inputs during the touchdown phase. Since those changes were implemented, major bounced landing incidents on the MD-11 have virtually disappeared. If you found this story worth your time, we have hundreds more. Check them out right here. And if you want to support what we do, consider subscribing. Today, over 100 MD-11s still fly, all of them hauling cargo. The last passenger MD-11 was retired in 2014. Pilots still call it by its old nicknames: the Death Star, the Scud. Names earned over 2 decades of fighting an airplane that always seemed to be one step ahead. But every MD-11 that lands today carries the lessons written in the wreckage at Narita. A simpler procedure, better training, a display that tells pilots what the back of the airplane is doing. And somewhere in that list of changes is the ghost of FedEx Flight 14, the accident that happened 12 years before Flight 80, that proved the MD-11 could kill on landing, that prompted a training fix which turned out to be not quite enough. The distance between Newark in 1997 and Narita in 2009 was 12 years, 2 pilots' lives, and one word that should have been in every recurrent simulator session but was not: go around.